Okay, so can you see my screen? Yes, okay. So let's start or continue discussing what we started discussing last time. What we started talking about last time was the idea of a covariance matrix. So a covariance matrix is a matrix which is defined as containing the pairwise covariances of the elements of a vector. So you have this vector. So the elements, the pairwise, there's a pairwise covariance, and the pairwise covariance is you record it and put it in this matrix. So the ijth elements of covariance of y, this is the matrix, is covariance of yi and yj. And so we discussed that the diagonal elements are just the variances, and so covariance of the variable itself is just the variance. And what we have is there's this alternative formula as well. So you can write the covariance as the expectation of a centered version of the random variable. You take the centered version of two random variables. So centering means removing the mean or the expectation. So I subtract the expectation from yi, the expectation of yi from yi. That gives me the centered version of yi. And I also have the centered version of yj. And then I multiply them and take the expectation. So this is the usual definition of the covariance matrix. And if you expand that expression, you get the alternative formula, which is expectation of yi yj minus expectation of yi times expectation of yj. And I would say two random variables are uncorrelated if this covariance means, sorry, the covariance, pairwise covariance is 0. Okay, so is that okay? Question. So now a couple of properties of the covariance matrices are listed here. So one is, so I'm calling the covariance matrix sigma. So that's the notation for the covariance matrix. It's not a summation, as I pointed out. So a covariance matrix is a symmetric matrix. The reason is that you can see here, covariance, the definition is symmetric. So if I interchange yj and yi, the covariance doesn't change. So I can write it here. Covariance of yi yj is equal to the covariance of yj yi. So that translates to this matrix being symmetric. Another way of saying a matrix is symmetric is saying that sigma is equal to its transpose. The other property is that if the random variables are pairwise uncorrelated. So pairwise uncorrelated means, what does it mean?
That means
sorry?
That means they are independent.
No, that's not the case. That's important too. There's a distinction between independence and uncorrelatedness.
Their covariance is 0.
Yes, so the key is that they're uncorrelated if the pairwise covariance is 0. They're not necessarily independent. I'm going to sort of emphasize that later in the course. So this means that the covariance is 0. Independence is a stronger assumption. So if yi is not equal to yj, then covariance of yi and yj is 0. Not necessarily independent. It's good to remember, not necessarily. Okay. So if the pairwise covariance, like they're pairwise uncorrelated, then these off-diagonal elements are all 0. And so the result is that sigma is going to be diagonal. So what are the diagonal elements of sigma?
Variance of yi.
yeah, so it's just going to be, so you get variance of y1, variance of y2, variance of yn, and the rest is 0. So in that case, you would have a diagonal matrix. Okay. The next idea is that I can write sigma in a nice matrix vector form. So using this formula for the covariance of two random variables, I can extend it to the vector case. So I would have this interesting formula. So sigma, which is the covariance of y, is equal to this expression. So the difference, so I'm subtracting, so mu is the mean of y. So what I'm doing is that subtracting the mean or the expectation from y. So y is a vector, mu is another vector, mu is its mean. So I'm subtracting the mean and then multiply it by its transpose. The difference with the scalar case is that I'm multiplying by transpose. So another way of saying is just covariance of y is expectation, and then y minus expectation of y, and then y minus expectation of y. Okay, so subtracting the expectation gives us a centered random variable. So another way, before looking at the other one, another like simple way of writing it is this way. So if I define y tilde to be y minus expectation of y, so that would be this guy. Then what I would get is, let me color this something else, for example. So this is, so this guy is this guy. And so what I would get is, so if you compare these two equations, so if you compare this and this, they're the same using this definition. Okay, that's an easier way of remembering the covariance, this formula. So if I take the centered version of y, which is this guy, then covariance of y would be the centered version, that y tilde times y tilde transpose. Does that make sense to people? So I'd encourage you to try to show this for yourself. So the way to show it, so show it. Evaluate expectation of y tilde transpose, the ijth element, which by definition is going to be the expectation of the ijth element of this guy. And so you take the ijth element and then you realize that that's the, so do this as an exercise. Show it as an exercise. Questions?
First transpose is inside the parentheses, not outside.
Yeah, so yeah, if you want, you can do this. It's a little bit clear. Yes. So, other question? This one's good. Other question? Okay, so what I want to do is ask you, so what is the dimension of y tilde? You want?
It's the same as y. It's just in Rn.
Yes, it's in Rn. So what is the dimension of y tilde transpose?
N by n?
Yeah, so this is n by n. And so when you take the expectation would have the same dimension. So the dimension sort of work out. Right? So that would be the sigma. Right? Questions? Okay, so the other formula for the covariance is this nice formula, which is this. And this you can get by expanding the other one. So you expand this, you get the other formula, and I encourage you to do it as an exercise as well. So this is going to be another exercise. And these formulas are similar to these two formulas. So this formula for the pairwise covariance and this formula. They're very similar, but they're the vector form of the same thing. So you would compute expectation of y transpose, and then you subtract mu transpose, and mu is just expectation. Just compare it with the scalar case, and you can see the similarity. But because we are dealing with vectors and matrices, you have to be careful about the transpose. Okay, questions? Okay, so one last point is that if I have a vector b, which is constant, and a scalar alpha, which is constant, and if I rescale y by alpha and then add b, this is a new vector. It's going to be an n by 1 vector. It has a covariance matrix. It's a random vector. And the covariance matrix is going to be alpha squared times covariance of y. So this covariance matrix is defined or given in terms of the covariance of y. You just rescale the covariance by alpha squared. And you can see that b doesn't appear on the other side. So this means that covariance matrices are shift invariant. So a constant shift does not matter. This is similar to the covariance of pairwise random variable. If you shift a random variable, you don't change the covariance of it with someone else or something else. And the reason is that all these things are defined in terms of the centered variables. So you can see the covariance is defined in terms of the centered variables. So once I take the expectation would have the same shift. And then I subtract, I remove that shift. And you can also see it in these formulas as well. So if you shift y by a constant b, the expectation would be shifted by the same constant. And so the centered version is going to be unaffected. So this is very important. Would be interesting to remember. So this constant shift. So it matters that it's non-random. Okay, constant here means non-random. Non-random. If it's a random quantity, then this doesn't hold anymore. Okay? Does that make sense? So for example, suppose I have some covariance of y, for example. Covariance of y is 2, 0, 0, 3. Okay, or maybe -1, -1. So that's the covariance of y. So I would ask, what is the covariance of y1, y2? What is the covariance of 2y1 -1, and then y2 would be a little bit tricky. We'll see that later. 2y2 + 3. what would this mean?
Just 4 times that entire matrix.
Yes, so this is just only the 4 times the covariance of y1, y2. Which is just 4 times 2 minus 1 minus 1. Okay, this is an application of that. So you can come up with many other examples. Questions? So what will happen if, for example, this is 3 instead of 2, that formula doesn't work. Part of that formula works. What part would work?
Removing the constant vector.
Yeah, so we could just drop this. But so you'd get that covariance of, for example, this would be the same as the covariance of this. But then the rest we'll see later. So later we'll see. Just actually right now, we're going to see an example. So that doesn't fall within this category of, or this formula doesn't help here. But this other formula, which we're going to talk about now, will let you compute that. Question about the previous slide. Now, this is one of the most important formulas, this lemma tree. And the idea is that this is, if you go back, we did similar things with, so I did similar things with the expectation. So if you have a random variable y, and then you have a non-random matrix A, you form this new random variable by multiplying A times y, A by y. Then there's this formula for the expectation. The expectation of A times y is A times the expectation of y. This is from linearity of expectation. I would like to do that for the covariance. So suppose I have a random vector y and a non-random A. So this A is non-random. Non-random. And then I form, as before, A times y. This is a new random vector. It has a covariance matrix. And this lemma says that the covariance matrix can be computed as A times covariance of y times A transpose. So this is a matrix product. And so the order matters. So you have to multiply them in this order. And it's a little bit counterintuitive, but you get used to it, okay? Does the statement make sense? Anyone has an idea of how to prove something like this?
We can use definition of covariance. In the
Yes.
you say the covariance is the expectation AY minus expectation AY time the transpose. And because we
Yes.
can get out A in the expectation and the definition of transpose, just change the A and Y minus expectation Y, and exactly we find this.
Okay, that's good. Yes. So that's what we're going to do. Yes. So I'm going to write it a little bit. Basically, what we're going to use this formula. And in fact, I'm going to try to use this one, which is equivalent. It's a little bit simpler. So I'm going to find what happens to. So if I have AY, okay, I would like to see what happens to the centered version. So if I call this vector, let's say X, then X tilde, I'll define it as X minus the expectation of X. We'll define it this way. So then what do we know about this vector? This would be AY minus the expectation of AY. Okay. Hello. So what was, can you say what would happen here?
expectation AY is A expectation Y, so you can take out A.
Yes, okay. Then what?
And factor A,
Yes, I'm going to call this y tilde. Remember, this is the centered version of y. So now the covariance of x, which is what we want, by that formula is expectation of this x tilde transpose. So I get the expectation of A times y tilde, and then A times y tilde transpose. What is the next step?
this transposes out of the parentheses,
Yes.
and then use the definition of transpose is become y tilde transpose A transpose.
So you get, I can drop the parentheses and I can so the transpose of this would be transpose A transpose. So when you transpose things, things get reversed. The product, so transpose of product is the product of the transposes. So that's what we get here. And this gives me A times expectation of y tilde transpose A transpose. Why can I do that? Is this valid?
Expectation y tilde transpose is exactly covariance of y, and before you say we can do it.
Right, well, why this is true? Why this step is true?
A is not random variable, so you can take it out.
Right, so I'm going to use, I'm using basically, if you recall, this formula. Right, so I have two matrices here. These are the A and the transpose here. And the role played by the A here would be the covariance, it's like the y tilde. So we'd have so example, expectation of A, y tilde transpose A transpose. So that would be my A here. That would be the B, that would be the C. This would be B, this would be C, this would be like A in this example. But then you can see B and C come out. So that would be these two come out, and then you get the result. So the notation is a little bit different here, but you get the idea. Okay, sounds good. So yeah, as was pointed out, this is just the covariance of y. So prove that the covariance of x is A times covariance of y A transpose. So that's this formula. Questions? I'll let you think a little bit about that. If you have questions, let me know. More questions? So here's an example. Suppose we have x1 and x2 being normal 0, 1 with covariance rho. And then I have that x is the vector X is just the vector that contains these two elements as their, or as its components. So it's a random vector, so it has a covariance matrix. The covariance matrix just contains the variances on the diagonal and then the covariance of x1, x2. As covariance of x1, x2 is equal to the covariance of x2, x1. So that would be the covariance matrix. So given this information here. Okay, so the variances are 1 and the covariance is rho. Okay. So now the question is, I have U is alpha x1 plus beta x2. And so this is a linear combination of the elements of X. And the idea is that I can write this U as this row vector times the vector X. Okay. So suppose now I want, this is a random vector, I want to compute the covariance matrix of U. So can I use this previous result here?
I think you can just think alpha beta as a 1/2 matrix and then apply the lemma 3.
Yes. Who's talking?
Xixing.
Okay. So yes, so I'm going to call this, let's say call this A. It's a 1/2 matrix. So what would be the covariance of U? Would be A covariance of X, A transpose. So that's X. So that would be alpha, beta, and then 1 row 1, alpha, beta, and then you can multiply and you get the result. So what is the dimension of covariance of U?
One by one.
Yes. So what is it exactly?
It's just a number, real number.
Yes. Does it have a specific name?
Correlation.
Correlation of what?
Of x, y, and x2. I don't really remember.
I just wanted to say that this is the variance of U. Okay, that's good enough. Right. So the covariance matrix, when it's 1/1, is just the variance. So this formula gives you a way to compute the variance of U. So if I ask you to compute the variance of U, you can compute the covariance matrix of U, which is the same, and then you can use that formula. So this formula gives you a way to compute the variance of a linear combination of a random variable. Okay. So lemma 3 allows us to compute the variance of a linear combination. Of random variables given their covariance matrix. Given the covariance matrix of the underlying vector. Just covariance matrix, we understand what this means. Put those, yes.
If alpha is equal to beta, then can you use both this or like do like, for example, in the previous one where we did like 4 times the covariance matrix? So could you write the answer as just the variance and also as the covariance matrix?
Okay, it's a good question. So anyone wants to answer that? So the question is that if alpha is equal to beta, can we also use this formula and say, so question is, alpha is equal to beta, can I say that covariance of U is, let's say, alpha squared times the covariance of X? Is that the question?
Yeah, because then we would be able to get both scalar and the matrix form of the answer. Would those be considered equal?
You tell me. Anyone has any comment about this? Is this okay? I wish I had a poll here, so I would ask how many of you think this is okay, how many think this is not? Maybe think a little bit about this, see if this is valid or not. Meanwhile, I'll try to see if I can make a poll here. Okay, someone has an answer. Do you want to talk about your answer?
So in the previous lemma, I think that was used when x times the scalar and the dimension of x stays the same, and in
Yes.
this case, u is of different dimension as x, so it's not applicable.
Right. So the covariance of U is going to be 1 by 1. Covariance of X is 2 by 2. So this thing is 2 by 2. So this can't be true. So what is wrong here is that U is not equal to alpha X. Okay. U would be equal to alpha X1 plus alpha X2, whereas alpha times X would be just alpha X1, alpha X2. These are two different objects. Okay. Does that make sense?
Okay, thank you.
No problem.
Wait,
So,
which
ahead.
which one was 1 by 1? And what was the dimension of alpha squared covariance of X again? That was the 2 by 1?
So what is the dimension of the covariance of X?
In that case, it would be 2 by 2.
It's always 2 by 2 because X is 2 by 1. It's a 2 by 1 vector. You can see the covariance here. So the covariance of X is not going to change unless you change X.
Okay,
So
and then alpha would be 2 by 1?
No, the
or
assumption
is alpha just us?
Yes, the assumption is alpha is a scalar. So alpha
Oh,
and beta
okay.
both are scalars, right?
Oh, okay. Okay, thank you.
So then you're multiplying a number by a 2 by 2 matrix, and so the result is going to be still 2 by 2.
Okay.
Right.
All right, thanks.
No problem. So can I use this result to compute the covariance? So I want to use this result to also be able to compute this covariance of this. Can I write this in that form? This is a different vector. So let me clean this up here. So can I use this lemma where should I write this? Let me open a page here. See if I can add add a page. Okay, so can we use lemma tree to compute covariance of alpha X? So covariance of alpha x is equal to the covariance of alpha times x1, x2, or it's just the covariance of alpha x1, alpha x2. Can I use this lemma to also compute that? Anyone? Yes? Is that a yes? Chen?
What I think is alpha times x1, x2 is basically just a diagonal matrix of alpha.
Great, yes. So I can write this as the diagonal times x1, x2.
You can use a lemma.
Yes, then you can use the lemma. It would be alpha 0, 0, alpha, covariance of x1, x2. And then transpose of this. So what is the transpose of this?
It's itself.
Yes, it's a self, so I'm going to delete the transpose here. So is this correct?
Yeah, because you just get alpha times the identity matrix, and then you just pull the alphas out. You get the same thing as alpha squared covariance.
Good. So I can write this as alpha. I'm going to write it as I2. This is the identity matrix of dimension 2. This is the covariance of, I'm going to write it as just covariance of x, vector x, and then alpha I2. So alpha has come out. These are scalars. I get alpha 2, and then you can just write many statements or just in one line. So this is just going to be covariance of x, because I is just the identity matrix. When you multiply the matrix by the identity matrix, you get back the same thing. So this formula also gives you that result that I mentioned. Okay. Go ahead.
Professor, can we
Yes.
say simply just alpha is a matrix 1 by 1, so we can use the lemma for that?
This is a good question. So covariance, so can we say alpha is 1 by 1 and say covariance of alpha times x, this is 1 by 1, right? And this is 2 by 1. Can we use the lemma, say this is alpha covariance of x, alpha transpose? Is that?
You can't, because you can't multiply alpha and x there, because they're not the dimensions
Right.
that correspond.
So the thing is that this is not a valid matrix multiplication, right? So this is assuming that this is this A times Y is a valid matrix multiplication, right? So you can't say that alpha times X is of that form. It's not like A times X. Does that make sense?
Thank you.
No problem. Yeah, so the right way to do it is write it like this. So that would be the A. And then we get that result. Okay, it was a good question. Okay. Other questions? So that formula is in fact very powerful. So if you just remember this, you can do many things with it. This lemma tree. Just go through the proof for yourself, and then we're going to see many examples. Here's another example. Any other questions? So let's do another example. So I have, I'm going to do it here. So let's do this here. So I have x1 and x2 standard normal, and there's the covariance as before, rho. And then I form a, you can see here, I form z1 is equal to x, z2 is equal to x2, and then z3 is equal to x1 minus x2. Okay, and then I form a vector z. So I have z is equal to z. Let me write it. Z1 is equal to x1. Z2 is equal to x2. Z3 is equal to x1 minus x2, and then I have z is equal to z1, z2, z3. That's how I define z. So this is a random vector. And I would like to understand its expectation and covariance matrix. So what is expectation of Z? I'm going to put a bar here to make sure that this is a vector, or denote that this is a vector. So what is the expectation of Z? How should we go and compute it?
Expectation of Z is 0, 0, 0.
Why?
And before we say if we want to find the expectation of the vector,
Yes.
we can define the expectation is exactly vector of expectation. So
Yes.
the expectation Z1 is 0, expectation of Z2 is 0, and Z3, because expectation is linear, is 0 minus 0 is 0.
Right, so this is 0, 0, and then this would be expectation of x1 minus expectation of x2. X2, that's the linearity expectation, and this is 0 because both are 0. Okay, so we get that this is the 0 vector. There's another way of doing it, which we'll see later, but this is good enough. So how do we compute? Is it okay with people? Any questions so far? So how about the covariance of Z? How do we compute covariance of Z?
I think the covariance of Z is a 3 by 3 matrix. The
Yes.
diagonal is just the variance Z1, Z2, Z3, and the
Yes.
other is covariance Z1, Z2, Z1, Z3, and
Yes.
Z2.
Yeah. So it's a 3 by 3 matrix. The diagonals are the variances. The off diagonals are pairwise covariances. So how do we compute those?
Can we just say, because if you write it out the column form for Z, and also like you substitute x1, x2, you can actually say that Z is the matrix, is a 3 times 2 matrix times a 2 times 1 matrix.
Okay, I do that. Then you're saying there's a matrix here I can do. Then what? Can you say that again?
So for the 2 by 1 matrix, it's just x1 and x2. And for the coefficient matrix, it's like 1, 0, 0, 1, 1, negative 1.
1, 0, say that
0,
again.
1. 1, 0, 0, 1, and 1, negative 1.
1, 0.
Oh, no, I
Can
mean,
you say it which way?
oh, so in a row, it's
Yes.
1, 0.
Okay.
And then the second row is 0, 1. The third row is
Okay.
1, negative 1.
Okay.
So I think in this way, then you can use the lemma 3.
Okay. Sounds good. Do people see this? Is this okay with people? So this is a matrix. If I multiply out the first row multiplied by this gives me x1. Okay, the second row here, this multiplied by this will give me this. And then this multiplied by this will give me that. So that's how we write it. And now we have it in the form that we like. So this is A, this is X, this is Z. So I've written Z as A times X. So then I can say the covariance of Z is equal to A times covariance of X times A transpose. Right, so you get 1, 0, 0, 1, 1 minus 1. Covariance of X is 1 row, row 1. And then transpose is 1, 0, 1, 0, 1, negative 1. So multiply it out, you get a 3 by 3 matrix. Okay, I'll let you do that. So that's how you can compute. Okay? Does that make sense? So how about if you wanted to, okay. How about if you wanted to do, good. Okay, how about if you wanted to do it directly? So if you wanted to like compute each component, I would need, for example, approach 2. This is approach 1. Approach 2. So approach 2, I would have covariance of Z would be the variance of Z1, variance of Z2, variance of Z3, and then covariance of Z1, Z2, and so on. Okay. So I have to compute these individual elements. So is there a way of doing that? Oh, what happened here? Interesting. I'm gonna do this solution of example 4 ahead. Okay. Approach 2 is I have to bring this up. Okay. So approach 2 to the problem uses the definition. Okay, so I have to I would like to compute, for example, so I know the variance of Z1 is 1, the variance of Z2 is 1, because these are just X1 and X2. So I know that X1 is normal 0, 1, X2 is normal 0, 1, and covariance of X1, X2 is rho. So how do we compute, for example, covariance of Z1 and Z2? So this would be covariance of X1. Z2 by definition is X2, so that turns out to be just rho. So this is the rho. How about the covariance of Z1, Z3? This would be more interesting. Covariance of X1 and X1 minus X2. That's Z3. So how do you compute this directly?
That one is covariance X1, X1 minus covariance X1, X2.
Yes. So covariance, right.
X1,
so what
X1. Sorry, continue.
Go ahead, go ahead.
I just want to say covariance X1, X1 is variance X1.
Yes. Okay, so that would be 1 minus rho.
Yes.
So why did this step hold? This is, so covariance is a bilinear operator. Bilinear. So what does it mean? It's linear in each of its arguments. So if I have covariance of alpha, let's say u plus beta, v, and z, this would be alpha covariance of u and z plus beta covariance of v and z. So I can expand, and I can do it in the second argument as well. So it is as if we are multiplying. So it's like alpha u plus beta v times z. If you expand it, you get alpha u z plus beta v z. So you can do this and then just look at this and see the formula looks similar. So for example, if I want to do covariance of, let's say, x1, suppose I want to do covariance of x1 minus 2x2 and 3x, 3 minus, we don't have x3 here, plus x2. what I would do is that imagine multiplying this. So how do you multiply this? You get 3 times x1 plus, let's say, x1 x2 minus 6 x2 x1 plus 2 x2, right? And so you get 3 x1 squared plus or minus 5 x1 x2 because they're similar plus 2 x2 squared. So this is going to be similar. So you get 3 covariance of x1 minus 5 covariance of x1 x2 plus 2 covariance of x1 is just variance. So I'm just going to write it like this. Variance of x1, variance of x2. So you can treat it as if you're doing product. Okay. Bilinearity rule for covariances. Does this make sense to people? Have you seen it before? You can do complicated covariances as long as they're linear combinations. Okay, yes. I see 1 yes, 2 yes. If it's a no, let me know. I'll come back and explain. Then I'm going to do another example. Let's say I want to do covariance of Z2 and Z3. This is covariance of X2 and X1 minus X2. What would it be? So that's X3, okay? That would be covariance of X2, X1 minus variance of X2. It's like multiplying things out, right? So if I multiply X2 by X1 minus X2, I get X2, X1 minus X2 squared, which you can translate it to this formula. Just trick, I would say. So that would be rho minus 1. Right. And how about variance of Z3? How do we directly compute variance of Z3? Which is just the covariance of X1. Sorry, the variance of X1 minus X2. How do you compute this? Let's say using the covariance idea I mentioned.
Is variance of, go ahead.
Right, let's do this. So to remember, this is the covariance of X1 minus X2 with itself. Okay? Right? Then how do you expand this? So this is like X1 minus X2 squared, which is just X1 squared minus 2 X1 X2 plus X2 squared. So that would be variance of X1 minus 2 covariance of X1 X2 plus variance of X2. So if you remember it this way, you shouldn't get any trouble, or you shouldn't get into any trouble, any like, never. So minus 2 rho plus 1, you get 2 rho minus rho. So you should be able to compute the covariances of any linear combination of random variables with any other linear combination of random variables. Just imagine multiplying the two as just expressions. Does that make sense? This is the trick again. Trick. Trick. The trick. Okay. Questions? So this way you can compute all of the elements and you should get the same result. So if you go back, so these are some of the calculations that I did. So that's, for example, this expression here. and so on, and then you can fill it. So you can fill all the elements, so that will be the variance of Z3. That's like these are the covariances and so on. So that's one way of getting this. The other one is the first approach that we mentioned, or was mentioned. So this is, you write it this way, then you get A covariance of X, A transpose. Okay, so they should give you the same answer. There are advantages and disadvantages. So this approach has the advantage if you want to compute the full covariance matrix. That gives you an easy way of sort of directly computing it, especially if you're doing it on a computer. This approach is useful if you just care about a single element here. You don't want to compute the full covariance matrix. I just, let's say, care about the variance. I just directly compute the variance of Z3. Or just care about the covariance of X1 or Z1 and Z3. That's what I compute. So they have advantages and disadvantages. But you should know both approaches. They're very useful. Okay. Questions?
Professor, because covariance matrix is symmetric, we need just to find half of them?
Yes, you just compute this part. That's a good point. So the variance says, and I can, for example, compute these three. Then I would know that, let's do this. So if I compute this, I would just know that this is equal to that. If I compute this, I would know that this should be equal to this. And if I compute this, I would know that this should be equal to this. So half of the off-diagonal elements are enough. So you can compute either one, and the other one is determined. Good point. Yeah, so this would be, for example, equal to the covariance of Z3 and Z1. This would be equal to the covariance of Z3 and Z2, and so on. Covariance matrix is symmetric. Okay, question? Comment? So I'm going to say that. Solution to example 3 continued. So let me know what this is. So this was part of the solution. Sorry, example 4. This is the second half of the solution. Okay, so go through this example. This is all you need to know about this subject. Okay.
Professor, can we go back to the direct, we compute directly?
This one, yes.
Yeah, so for the part in blue, for the last term, like for example, the covariance of x1 minus 2x2, 3x1 plus x2, should the last term be minus 2 variance x2?
You're right. So this is 2, 3x1. So what happens if I multiply here? I would get let's check. Yeah, so that would be a negative sign here. And also here. Negative. That's good. Okay. Yes. Thank you. Whatever this does, the covariance does the same thing. That was a good point. So it's not necessary that the variances always appear with positive coefficients. Okay. If you're computing the covariance of something with itself, like this, then the variances appear with positive coefficients, but not in general. So if you compute the covariance of some linear combination with another linear combination, these were different. then you could have variances appear with negative coefficients. That's fine. Questions? Other questions? Thank you. That was a good catch. I'll do this. Anything about this or this? Okay, seems not. So let's move on to another information, a piece of information about the covariance matrix. So this proposition is another interesting fact about covariance matrices, and it just says that the covariance matrices are positive semi-definite. So do you remember what positive semi-definite meant? What does positive semi-definite mean? This proposition says that any covariance matrix is always positive semi-definite. All eigenvalues greater than or equal to 0. Yes, that's one of the equivalent, let's say, characterizations. What is the defining characterization? The definition that we gave, it was different. It's equivalent to all the eigenvalues being non-negative. Well, what was the definition? You don't remember? It was a technical definition.
It's like the inner product between x and ax are greater than or equal to 0.
Yes, so let's say sigma is covariance of y. Would like to show that sigma is positive semi-definite. What I can do is use the proof for any. I'm going to take a instead of x. In Rn, need to show that A transpose sigma A is non-negative. Okay. So I'm going to go here. A transpose sigma A is just A transpose covariance of Y times A. So does this look familiar to people? So if you go back to this lemma. So A transpose covariance of YA. If you stare at this and the lemma, can you say something about this? The lemma tree, yes. So that's lemma tree. So what about lemma tree? Can you say that this is equal to something interesting?
It's equal to the covariance of A transpose Y.
Covariance of A transpose Y. Yes. Example. So this is going to be equal to the covariance of, covariance of A transpose Y. So what is A transpose Y? What are the dimensions of A transpose Y? So Y is in Rn as well. So dimensions of covariance of A transpose Y. But what is A transpose Y? The dimensions.
1 by n.
You have
Or
to
1
give
by
it
1.
another 1 by 1. Yes. So what would this quantity be? Does it have another name?
The variance.
Yes. So this would be the variance of A transpose Y. So can the variance be non-negative? So can the variance be negative?
No.
No. So this variance is always non-negative. And this proves that A transpose sigma A is non-negative. So we have proven that this quantity which is equivalent to the variance of A transpose Y, is always non-negative. So this proves that sigma is positive semi-definite. See, this is easy. That's basically the same proof. So this is an interesting fact, and we just proved it using that lemma tree. So covariances are always positive semi-definite. Then you can use the other alternative characterization. So now you know that all the eigenvalues of a covariance matrix have to be non-negative. That you know for free. Questions about this?
Sorry,
Yes.
could you repeat how it went from covariance of Y to covariance of A transpose Y? Like I get the lemma 3 setup with the A transpose covariance Y. Oh, it was in the example.
Right, let's go here. That's where is it? Yes, here.
Yeah, so I was wondering how you got from covariance of Y to covariance of A transpose Y again, because I know it has A transpose A, and then yeah.
No, I didn't get from covariance of Y. So what I'm saying is that A transpose covariance of Y times. So I'm saying this quantity is equal to this, right? So the reason is I'm applying this. Take this to be A transpose, and then A transpose would be A, right? So then this is A transpose Y. So this formula just says covariance A transpose Y.
Oh, it's just from the from the lemma. Okay.
From the lemma applied to, yes. So.
Okay. Okay, I thought it like meant like you had to do something, but
No,
okay.
apply with A being A transpose, yes.
Okay, thank you.
No problem. Yeah, so this lemma is fairly general, and you can get interesting things out of it by choosing a property. Okay, other questions? Okay, so we have still a few more minutes. So one point that I want to make here, which is not that relevant in this course, but just because you're here and you might need it later, I'm just going to point it out. So covariance matrices are always positive semi-definite. But if you recall, we also defined something called positive definiteness, or strictly being a strictly, so this inequality being a strict. So if this inequality is strictly positive, for any A that is non-zero, then we call the matrix positive definite. And this need not be true in general, okay? So it could be that A transpose covariance of YA is 0 when A is non-zero. In that case, the covariance matrix is not positive definite. It still is positive semi-definite, but it's not positive definite. So what does this case mean? So I have a non-zero vector such that this holds, and we just saw that this side is equal to this side. So this means that I can find a non-zero vector A. So this is saying there exists non-zero A such that the variance of A transpose Y is 0. Okay, that's what our calculation shows, because these two expressions are the same. A transpose covariance of YA is the same as variance A transpose Y. And then you can verify that this means that A transpose Y, anyone knows what happens if a random variable has 0 variance? What can we say about that random variable? Anyone? Yes, constant. So Chan points out that, so this means that this is going to be constant with probability 1. That's what I'm writing here. So this is a fact from probability. A transpose will be constant with probability 1. So this is saying a linear, so A transpose Y is a general linear combination of the elements of Y. So this is saying that I can find a linear combination of elements of Y that's a constant, not random. Okay, so this is non-random. Constant means, this means non-random. And this is a pathological case because A is a random vector. Generally, it's just distributed over the whole space, RD. But this is saying that in this case, A basically lies on a lower dimensional subspace. It could, for example, lie on a plane, or it could lie on a hyperplane. So this means this is like saying, for example, all my points Y are going to be on a plane. For example, if you're working with R3, so if Y is R3, this lemma is saying that there exists some plane or some subspace that could be a line, such that Y just lies entirely on this line. So it's not super random, let's say. It's somewhat random, but there is some structure to it. This usually doesn't happen. So that's what I'm saying. It's a pathological case. So you get like points exactly on this. They're randomly distributed on this, but they're all on this line. Or they're randomly distributed, but they're all on this plane. They're going to be always on this plane. So if this case doesn't happen, then your covariance is positive definite. Okay, and if this case happens, because this is 0, then you can verify that this implies that A is an eigenvector associated with 0 eigenvalue. Okay, so this in the pathological case, there is a 0 eigenvalue, or there are multiple 0 eigenvalues. There are non-zero eigenvectors associated with those. And then those eigenvectors are such that if I multiply, so A transpose by Y, then I get a constant. And this means that they're on a lower dimensional subspace of the whole space. This is a little bit advanced, so I'm not expecting you to perfectly absorb this, but just remember this. And if you have questions, I'll be happy to answer. Let's say maybe start of the next lecture or in the office hours. But this is like, I would say, bonus point. But the thing that you have to remember is covariance matrix is always positive semi-definite. This is the coordinates. Okay, questions? We're a little bit over time. No questions? Okay, we can hopefully come back and talk on, or continue on Wednesday. Just please don't forget to fill out the doodle about the office hours. And also please tell your friends to fill that out. Okay, thank you. Thank you guys. See you on Wednesday. Bye-bye. Bye. Goodbye. No problem.